Welcome to the public presentation for Wilson Park Lake. I am Andrew Frana, the TMDL project lead for Wilson Park Lake, and I'm doing this presentation on behalf of the Water Quality Monitoring and Assessment section led by Roger Bruner. As you can notice, we are in the public notice comment period will go through March 7th of 2022. So what that means is you have until then to send any official public comments to roger.bruner@dnr.iowa.gov. And with those public comments, you'll have an official response from us at DNR. We will include both the comment and the response in our document when we send that to EPA for our final approval. If you have more technical based questions regarding the modeling in the document, please feel free to reach out to myself at andrew.frana@dnr.iowa.gov. And I can get back to you just the same. Before we go into the document a little bit, I want to talk about some terminology that we'll use throughout the document and the presentation just to familiarize ourselves with some ideas that will be relevant. One of those is, what is a watershed? We're going to talk about watersheds quite a bit. That's the area that we're looking at. So if you look at a vicinity map around Wilson Park Lake, you can see this little black area that's highlighted. That is the watershed. So what that means is the storm comes along, it's raining here, it's raining here. That rainfall follows this path out. If the rainfall falls within this boundary, all of that rainfall will end up in the lake itself, and that rainfall and the pollution on the land will impact the water quality of the lake. So that's the area that we're looking at. That's the area that's important. That's the area that we're quantifying. And then every map that you'll see in the document and this presentation will have some components. They'll have titles, they'll have north arrows, inset to where we are in the state of Iowa, a scale to show the relative distance. You can see here that Wilson Park Lake watershed's relatively small compared to some of the projects we do, but nonetheless, it's still important. And then we have a legend here with all the relevant pieces of information within the map. We have the watershed, the lake, and then definitions of rivers, roads, and public lands. If we zoom into the watershed itself, we'll see that same shape, that same watershed. Again, if rainfall falls within this area, that rainfall will eventually end up in Wilson Park Lake and could impact, for better or worse, the water quality. So this is a land use map. It's going to be useful to show what's going on in the watershed. We can look at the map, see that green is parkland. This yellow brown is corn or soybean, so row crops. And then we have various pieces, pasture, farmstead, and different types of grassland. And again, this map will have the same components. It'll have the north arrow, the map inset, the scale, and then the legend. If we zoom in one more time, another important map in the document that we'll talk about is just the map of the lake itself. We have here different components. We have the deepest point of the lake here, which will be important later on. And then you can just see parking areas, boat ramp, the inset with all the relevant information, depth, area, volume, things like that. Some more terminology. Okay, impairment is going to be brought up a lot within the document itself and the presentation. When we say impairment, what we mean is that the lake is not meeting water quality standards. It's not meeting water quality expectations. It could be doing better. So any of these documents that we write will be impaired. We'll figure out why it's impaired, what we can do to mitigate the impairment and improve the water quality. All those impairments are in a list that we put out every couple of years. We go through them and try to fix them one by one. Two important sources of pollution that we will discuss. First, point source. Point source pollution you can think of conceptually as anything that comes out of a pipe. Although it's not quite technically correct, we can think of point sources as anything that has a permit to discharge. That can be factories, cities, different things like that. But conceptually, anything coming out of a pipe, in reality, anything with a permit. So anything that doesn't have a permit then would be non-point source pollution. These are more diffuse across the landscape. a little bit harder to quantify and model. And since we have no point sources in the Wilson Park Lake watershed, all of the relevant pollution will be coming from non-point source pollutions, non-point source pollution, sorry. So we brought up the word TMDL already, or the acronym TMDL already. What does that mean? I am the TMDL project manager, but let's look at that. The definition is really long-winded, identifies the maximum amount of a pollutant that a body of water can assimilate while still meeting water quality standards or not being impaired. What does that mean? Let's look at an example here. I've always found this image to be illustrative of how I see what TMDL stands for, total maximum daily load. And really, we're trying to find out the tipping point of what this watershed needs to reduce its pollution and how to be able to meet the expectations. And why I think this image really does that is if you can imagine this pack mule at some point had no boxes on this cart and he was able to pull the cart without any issue, run around all day, and he'd be fine. As we start adding boxes, it gets harder and harder for him to do the work. He can, and he only has the point, he has a point where he can not pull the cart along. So its function is obviously at a comical stage where there are so many boxes, he's flipped up in the air. So clearly he can't do any work. Now, if you think about this as a lake system and the boxes as boxes of pollution, you can put a box of pollution into the lake and it can meet expectations. You can put 2 or 3 or maybe even 4 or 5, but eventually we put too much pollution in the lake and we're not able to meet those expectations. We're not able to do the work that this lake is expected to do. And that results in things like algae blooms and impairments. So this is the idea here, is how many boxes of pollution we need to pull out of the cart or pull out of the lake on an annual basis to be able to have the lake perform how we want it to. And that thing you also find in the document is that we've included an implementation plan. We have extensive conversation about implementation ideas. They have their own chapter in the document, and they are meant to be a springboard for local conversations to figure out how best to implement practices on the watershed to help reduce that pollution, to help pull those boxes of pollution out of that cart. And those two elements together, we combine them in the actual identification of the total maximum daily load, that specific number, and that implementation plan. Those two concepts combined are the water quality improvement plan. So you'll notice the front cover of the document. This is the Wilson Park Lake Water Quality Improvement Plan. We might refer to things time to time as the TMDL, just as shorthand. And so sometimes those terms are used interchangeably. But what we mean when we say water quality improvement plan is that not only is there the actual number, total maximum daily load, and the calculation that's behind that, but we also include information that would help lead to any sort of plan that's located within an implementation plan. One last thing before we get into the meat of the presentation, I just want to show an example of a chart. We'll see these throughout the document and in the presentation. They might look intimidating, you might not know what they mean right away, but we'll try to explain each piece of the chart up front so you can gather the information that's relevant. So if you look here at the bottom x-axis, we can see it's years from 2011 to 2020. Those are the years that we've collected water quality data within Wilson Park Lake. And then we see here on the y-axis something called TSI values. I'll explain that later, but we can see that they range from 30 to 90 in this lake. And then we have these different dots corresponding to TSI of Secchi depth, TSI of chlorophyll A, and TSI of total phosphorus. We'll define those all later. And then we have this big red line right in the middle. So one could assume that either above or below the big red line will be important. And we'll explain why later, but just wanted to put this chart up here front and just kind of let you absorb what it is we'll be talking about. The outline will consist of the water quality improvement plan. Then we'll go into a description of Wilson Park Lake and its watershed. We'll talk about the water quality assessment of the lake itself. We'll go into our TMDL development, and then we'll talk about some implementation planning strategies that can help mitigate the impairment of Wilson Park Lake. So the water quality improvement plan, when we develop those, at the very beginning, we have to first monitor and assess a water body. We have to determine if that water body is impaired or not. Is it meeting its expectations, or is it good to go? Or is it not good to go? Then we'll draft the water quality improvement plan by determining the potential pollutant sources. Is there non-point source? Is there point source? We will calculate the total maximum daily load, and then we'll add that implementation plan, a list of potential solutions and best management practices. From there, we'll go to the step we're on right now with the public meeting. We'll be asking you for public review of our documents and give you the opportunity to comment. And after that, it's really down to local involvement. It needs to be led locally, boots on the ground, to make those implementation strategies and practices work. And then from there, we'll have to continue monitoring the water body to ensure that water quality is indeed improving. So if we look at Wilson Park Lake, you'll see that it's fairly small. It's about 17 acres. And the maximum depth, this red point right here, where we take our water quality readings, is at 18.7 feet. The mean depth is about 7.3 feet, and the volume is 125 acre feet. So what that means is if you had 125 acres, or roughly 125 football fields, the water from the lake would be 1 foot tall. That's 1 acre foot over 125 acres. If we look at the watershed itself, talk about the land uses, we can see that there are a variety of land uses in the Wilson Park Lake watershed. We have corn and soybeans up here in the uplands, and then we have closer to the lake itself, we have parkland, pasture, which is a type of grassland, alfalfa, another type of grassland, and then we have some long-term CRP that we also model as grassland. Then we have a few parts of farmsteads, and then the road itself. In addition to land use, we look at soil type to determine how that will impact water quality downstream. You can see that there are several types here. Adair, Clarinda, Clearfield, all make up the soil type map of Wilson Park Lake. Another important parameter that we look at is slopes. So think of slope as how steep of a hill or how flat of a surface we have in the watershed. We have different classes. We have Class A from 0 to 2. We have Class B from 2 to 5%, Class C 5 to 8%, Class D, Class E, and then Class F is anything above 30%. We can see here that the uplands again are fairly flat, getting steeper as we go towards the lake itself. We can see there's some hills here. That's flatness right here is a road. Then we have the back of the dam right here. We can see that the average slope of the Wilson Park Lake watershed is moderately steep. So that will factor into how much erosion we get off the landscape. So we've talked about the lake, we've talked about the watershed. Now let's talk about what's wrong with Wilson Park Lake. So overall, there are water clarity issues from algae. That's the main issue here in this lake. Where do we get that data? Again, we look at the watershed. We have our ambient monitoring site here, which is the deepest point in the lake. We'll go out there a couple times a year. We'll collect water samples, send them to a lab, and test for various water quality indicators, including chlorophyll A, which you can think of as algae, Secchi depth, which you can think of as how clear the surface of the water is, and then nutrients like nitrogen and phosphorus. So if we take that data and we do a water quality analysis on it, we will go from there and determine what determines poor water quality and why. So again, we have too green of a system right now, too green, too much algae. It can also be too murky at times, but the algae is mainly the issue. And what we have in this photo is a person taking a Secchi depth reading. So what we have on the right here is a Secchi disc. If you can imagine a disc with alternating quarters of black and white with a tape measure running the length of it up, you lower that into the water, And as it goes down, you determine if you can see the difference between the black and the white quarters. And once it's down deep enough where you can't really tell the difference between the two colors because of the cloudiness of the water, that right there is what's called the Secchi depth. So if you can imagine crystal clear water, that depth might be fairly deep, all the way down to the bottom, but fairly murky water, or if you have algae blooms or stuff like that, you might have a really shallow Secchi depth because of the turbidity issues in the water quality issues. So again, we're going to bring up this chart that we had at the beginning. We're going to talk about water quality and what that means in the watershed. Just to cue this up, we have going back to 2002 all the way to the end of 2019. On the y-axis here, we have TSI values. So TSI stands for Trophic State Index. And we're going to talk about that with some different parameters. Trophic State Index, just think of that as the level of productivity in the lake. By productivity, we mean the ability for aquatic plants or algae to thrive. So the lower the TSI value, the less vegetation issues there will be in the lake, the higher, the more issues there will be. So we call that high values eutrophic or hyper-eutrophic. So that just means lots of growth, if you know some Latin. So if we look at where we want to be below this level of 65 right here. That's what we determine our impairment value. Anything below 65, if we take the median of our water quality data for a certain time period, we can either have that be impaired if it's too high or be delisted if it's low enough. So when we start to overlay our data from the years, we have our annual values here of these blue diamonds, which are the TSI, Trophic State Index of Secchi depth. So that's that water clarity. We have our Trophic State Index of chlorophyll A. So just think of chlorophyll A as a stand-in for algae. And you can remember that by chlorophyll, plants. And then also we have green diamonds here to kind of show vegetation as well. The last parameter we're looking at here is the Trophic State Index for total phosphorus. We have those listed as purple squares. So if you look at overall, we can see that we do have some issues with all of these indices above our impairment limit. So we can see that we do have water clarity and water quality issues in Wilson Park Lake. So we're just going to back up. Again, what is a TMDL? We did the pack mule and cart analogy. Again, the TMDL consists of a target, water quality target, the equation, the actual calculation of the limit itself, and then allocation. Where does that pollution come from? Where do we have to take it away in order to meet our water quality expectations? So in Wilson Park Lake, our target is phosphorus. This phosphorus can cause excess algae because phosphorus is a nutrient. So if you just think of it as fertilizing the lake, that algae is going to grow. Phosphorus is then transported by surface runoff and groundwater flow from the watershed down through the landscape to the lake itself. So if we reduce that sediment and runoff to the lake, we could be reducing available nutrients to those algae blooms. So we have our target of phosphorus. We have our target sources of where that phosphorus is coming from. At the beginning, we talked about point sources and non-point sources. So again, point sources are anything that's permitted to discharge into the watershed. So think of those as wastewater treatment plants, direct outlets, and then MS4 communities or larger communities. And then we have non-point sources. So anything that is not permitted or more diffuse across the landscape, think of that as erosion from fields, as atmospheric deposition, wildlife in the watershed, things like that. So like I said earlier, those potential point sources, we actually have none in this watershed, so we don't have to worry about those. So in our calculation, that will be a 0. If we look at the non-point sources for Wilson Park Lake watershed, there's several of them, and right up top, land application of manure and runoff from fields is going to stand out as the big one in this watershed. But we also have direct deposition of manure in streams and pasture land. We have grazing animals, wildlife, urban runoff from some of these farmsteads and roads. We could have some failing septic tanks. And then finally, closer to the lake, we could have gully and stream bank erosion that is falling into the lake itself. So we have our target, phosphorus. Now let's talk about our equation, or you can think of that also as a budget. So when we look at that equation, a budget will have fixed bills, like your rent, or mortgage, your utilities and things like that are the same every month. And then variable bills, things like groceries, what you spend on clothes, entertainment, things like that. And then unexpected costs. Do you have a vehicle that needs to be fixed, things like that, medical issues. So when we compare that to a TMDL, we have our non-point sources as our load allocation, our point sources as our waste load allocation, and then we have a margin of safety right here. So just think of waste load as fixed bills, something that would stay the same throughout the year. Our load allocation or our non-point sources, that's something that would be changing. And then just because we want to cover ourselves, we have a margin of safety to ensure that we are being conservative enough with our TMDL value to ensure that water quality is improved in the lake. So our TMDL components, again, point sources, again, that's waste load allocation, non-point sources, load allocation, and then our margin of safety. If we put that all together, we have that equation again, waste load plus load allocation plus margin of safety. Again, the waste load or point sources in the watershed are 0. The load allocation for Wilson Park Lake is 122.8 pounds of total phosphorus per year. And then again, our margin of safety is about 10% of that total value, so 13.6 pounds of total phosphorus per year, giving us a total maximum daily load of 136.4 pounds of total phosphorus per year. Now, what does that number mean? What do we compare it to? I mean, that seems kind of low, but you have to think of the amount of sediment that runs into the lake to get to that number of the tons of sediment that go into the lake to get to that number of pounds of total phosphorus. And how does that compare to the current existing phosphorus load? So currently, we looked at water quality data. We have about 271 pounds of total phosphorus per year going into the lake. Now, if we want to get down to our TMDL value of 136.4, we have to have about a 50%, a little bit less than 50% reduction to get to our TMDL value. That seems like a lot, but it's not. It's very doable over a several year period, over lots of implementation, planning, and future monitoring. So we talked about our target, we talked about our equation. Now let's look at allocations. Again, where is that phosphorus coming from in the landscape? So if we look at our TMDL load sources in the document itself, we have it listed out as coming from pasture land, row crops, grassland, forests, groundwater, and then all others. We can see that by a mile, row crops, which would be sheet and rill erosion from corn and soybeans, has 208.8 pounds per year, which is about 77% of the phosphorus loading. So that's going to be where we want to target our reductions in the future, since that is the main source of phosphorus. So how we're going to do that, we're going to talk about implementation planning. This can include possible solutions, best management practices. Again, we have to encourage local participation, and then we have to allow for future monitoring to ensure that water quality improvement is indeed happening. So when we talk about best management practices, we talk about land management, preventing erosion, preventing phosphorus from leaving the land. So we can do that. That'll keep phosphorus moving. It provides benefits both to soil and water quality. So land management can improve crop yields in some cases as well. Some examples of this would be conservation tillage, no-till, cover crops in the fall or spring, perennial strips, CRP, and then a big one could be nutrient and manure management. So when are we placing those nutrients, how much, how, just to make sure that it stays in the soil so you get your most bang for your buck too. You're not letting money go down the drain. An example of that would be no-till farming here. You can see that we have soybeans planted over corn from the year before. That corn stover acts to slow down energy from rainfall coming in, which can keep that soil in the area, reduce erosion, and increase soil quality by having those nutrients stay in the soil. Another BMP we can talk about are structural or mitigation practices. So think of that phosphorus or soil erosion already happening. We can stop that phosphorus from reaching the lake. Several examples of those include riparian buffer strips, saturated buffer strips, grassed waterways, sediment basins, and wetlands. Talking about sediment basins, we have an example of one here. The goal is after a rainstorm, it will catch and detain that water, slowing it down before it gets to the lake. We can see then that these heavier particles, these sand and silt particles will settle out and into the basin and then not reach the lake, which can also prevent phosphorus from reaching the lake. One last best management practice strategy would be in-lake remediation. So remediation would mean fix existing issues already in the lake. So let's say there's already phosphorus in the lake. What can we do to take that pollution out to get the lake water quality back to where we want it to be? Some examples of in-lake remediation would be fisheries management, shoreline stabilization, and targeted dredging. Fisheries management would be removing rough fish like carp who can stir up the bottom of the lake and then resuspend some of that silt, sand, and clay, and potentially phosphorus. Targeted dredging would be an example of potentially draining the lake and actually scooping out that material with heavy equipment. That tends to be fairly expensive and wouldn't really be the best bang for the buck in this watershed. So we're looking at shoreline stabilization here, making sure that those shorelines don't slowly just settle and sink into the lake and cause more soil and phosphorus buildup. So then the next steps after we've done that, we have to continue to monitor the lake in order to see that the water quality is improving. Are what we're doing actually doing something? And that can be done by having a locally led effort. We need to have involvement for greater success, promote awareness, create a watershed group around your stakeholders and your shareholders in the lake, develop watershed management plan. So there could be some sort of funding opportunities, and then finally implement those water quality improvements. And lastly, the DNR may be able to provide technical assistance. One last time, if you do have official public comments, make sure you get those in by March 7th of 2020, and you can send those to our supervisor, Roger Bruner. His phone number is 515-310-0247, with his email being roger.bruner@dnr.iowa.gov. And if you have technical questions regarding the modeling, feel free to send them my way. My phone number is 515-725-8396. And my email is andrew.frana@dnr.iowa.gov. Thank you for listening.